So good morning to everyone. My name is Tomaso de Cola from the German Aerospace Center, and I'm the coordinator of the 5G-STARDUST project. And I'm very pleased to have today with my colleagues that are going to present their parts in a couple of minutes to show the main achievements that were accomplished in the course of the 5G-STARDUST project. The 5G-STARDUST project essentially closed its activities just a few weeks ago, before Easter, on March the 31st, after an exciting and long journey that lasted roughly 39 months. But I think it's much more interesting and easier to start showing what we did. Before doing that, just some information about, let's say, how this webinar will work. I think you have already attended many other webinars in the context of SNS project, so I'm pretty sure you are quite used to, let's say, to the house rules, but just to make sure we are all on the same page. As you probably have already observed, the webinar is being recorded, and the recording will be distributed in the next days. Only speakers are allowed to use the camera, microphone, and share the screen. And as a matter of fact, the way of posting questions, making comments, and so on has to happen through the QA box that you can see on in the menu of Zoom, so that you put the question there, and after each of the presentation, the corresponding speaker will post there the answers. Obviously, if time allows and some additional clarifications are needed, some live discussion might happen at the end of the session, so that the corresponding speakers addressing those questions may say a few words more just to clarify the points. If, again, we are running out of time and there are still some interesting points you'd like to make, of course, you can address all the questions to us by email offline, so that we'll be very happy to come back to you with all the necessary clarification you'd like to know, or any other further points you'd like to discuss with us. This Saturday is finally time to start, and before doing that, obviously, I would like to quickly tell you what is ahead of us in the next 60 minutes or so. I will quickly give a project overview, so the project, what it is in a nutshell, and then jumping to the interesting part. So first of all, we will have a short review of what were the scenarios that were considered, and then the architecture that was developed according to a very formal and precise system engineering approach, starting from the user mission requirement and then jump into the system requirements. System requirements that in turn are the essential elements to go forward in the actual technical development that is now presented in two main pillars. We have first the radio technologies and then the networking operation. Obviously, because of the lack of time, we were not able and we won't be able to address all single activities, the highlights that were achieved in the course of the project, but we had to select some of those that we considered the most interesting and for which more results and more dissemination initiative were achieved. Last but not the least, there is the part related to the proof of concept and the final demonstration, because one of the main outcomes of the project was indeed the one of achieving a POC with a lab demonstration and a final demonstration that was conducted in November last year. Here, in the course of this webinar, we won't be able to run another demonstration because this would necessitate some more time, but we will be happy to show what were the main achievements and the lessons learned. And then at the end, there will be a kind of final wrap-up to recollect the main impression and lesson learned all of us had during the project, and some take-home message towards the possible future projects still working in this context. The overview. Okay, so project name 5G-STARDUST, and as the name suggests, we are going in the direction of integrating terrestrial and non-terrestrial networks, because it's dealing with the satellite and terrestrial access for distributed, ubiquitous, and smart telecommunication. And this project was originated by the first SNS call in Stream A, ubiquitous radio access, that has a strong accent on how we can achieve unification or convergence between terrestrial and non-terrestrial networks, mostly having in mind the evolution of 3GPP towards 5G advanced. Nevertheless, in the course of the project, our mission and our objective was also to project ourselves more in the direction of 6G and then see which kind of gaps or technology solution are needed to pave the way towards NTN being part of 6G from day one. And in that sense, the objective was indeed to develop and demonstrate such an integration according to the different elements that are going to be discussed in more details by the colleague in the next hour or so. The consortium was made up of 10 partners distributed across the 6 countries, with DLR being the project coordinator, myself, the technical manager was from Thales Alenia Space, France, and as such we had a good balance across all partners between academy and industry, representing both the satellite and the terrestrial part, with the manufacturer and operator, as you can see here from the list of the organization. The key objectives, as quickly reported before, were pretty much about achieving a 5G-based satellite network, and in particular we were kind of interested and focused on analyzing to which extent we can achieve 5G in space by exploiting the capability of onboard processing satellite system, and with that also the storage capability that can be offered on board. Then obviously there are a number of additional points, especially related to more effective user-centric beamforming, achieving a full-fledged 6G or 5G-based architecture, building on self-organized networking principle, and then obviously to exploit a data-driven AI-based concept, especially for what regards to the optimization of multi-connectivity and resource allocation that will be separately addressed as part of radio technology and networking operation in today's presentation. Last but not the least, there is obviously a strong interest in to see how this new landscape, that is the integration of 5G/6G with NTN, may be important for the positioning of the European industry, and as such also try to draw a kind of roadmap for the future development and the possible exploitation at the business level. That is obviously as an important component from exploitation and the cost analysis. This latter part, however, is not much addressed in today's presentation, but can be found in the corresponding deliverables that have been completed in the last months. Key technologies, but I think this is quite straightforward based on what I've just said. Regenerative payload, unified radio interface, software self-organized network architecture, and then the end-to-end AI-driven network design. Concerning the scenarios, obviously this was the very first point. Before jumping to this, I think it's worth spending a few words about the general methodology. As mentioned before, a very formal and precise system engineering approach was conducted, so that starting from the scenario definition, the user and mission requirement, we have in turn defined the architecture, and as a part of this exercise, we were able to identify the specific sub-modules, sub-blocks of such an architecture that belonged either to the radio interface or to the networking function, and these have been developed accordingly. Part of these elements, after being developed, have been eventually integrated into the POC, so in the proof of concept. I'm saying part of them just because not of them reached the necessary maturity, so that some of them were demonstrated within the corresponding work packages in terms of dedicated simulation or standalone tests, but while the other were really part of the larger demonstration that happened as a final result of the project and reported as a lab demonstration. In terms of use cases and scenario, there are these two macro categories, dual connectivity and architecture and service distribution scenario, that allowed us to define the main subset and the scenario to be further assessed in the course of the project, although I said only a couple of them were retained for the final demonstration in order really to highlight what is the added value. Of course, this was also done in relation to the fact that because of time and budget limitation, we could not really demonstrate everything with the large campaigns. Neither this was the objective of the project. For what regards to the satellite architecture, as I was saying before, this is a LEO satellite constellation, obviously, with onboard processing capabilities in order also to see how or how far we can push our design so as to include 5G capabilities on board. Our focus for this project was indeed that of achieving or at least embarking a full G0B in space, although as a matter of fact, obviously, we also investigated a little bit which other functional split could be meaningful, and this is going to be presented in a couple of minutes by the colleagues. And in particular, one split was also considered for the actual demonstration in lab. This is, in a nutshell, to represent a little bit a possible example of different functional split that we are quite aware of that can be considered. Of course, there are also sub-options. I don't want to spend too many slides on this because, I said, this is something to be further presented by the colleagues. The point I would like to stress is about the fact that we have a constellation. Satellites are interconnected by means of optical-based inter-satellite links. And then we have the traffic that goes bidirectionally to the final users on ground, through ground station and so on. Obviously, is not a satellite-only project. There is an important component also coming from the terrestrial infrastructure, so that in this project, the objective is really to demonstrate what are the challenges, but also the potential of, I would say, more importantly, the potential of having a unified 6G or 5G ecosystem where terrestrial and non-terrestrial network may coexist. In the course of the project, obviously, we had also a focus on the ORAN architecture, try to understand the different components, which role they may play in the general functioning system with respect to the different functions being elaborated. And in that sense, we also had obviously an important attention on the application of a data-driven concept, especially for what regards to the exploitation of artificial intelligence optimization of algorithms. So this was, in a nutshell, the first part. Then I would like to give the floor to the colleagues for what concerns the radio technologies part. So please, the floor is yours.
Thank you, Tomaso. Good morning. My name is Màrius Caus, and together with my colleagues Alessandro Guidotti and Luis Blanco, we will present the main research outcomes of the project within the scope of radio technologies, focusing on beam management, user-centric beamforming, and AI for radio resource management. You can go to the next, please. Yeah, I will cover the first part. But before going into details, I will first introduce the problem under study. In this sense, in the 3GPP context, beam management refers to the procedure that allow the UE and the base station to align antenna beams. And in this project, this presentation, I'm going to focus on the operations performed by the base station to scan users in the initial cell search. The main challenge in the 5G-STARDUST constellation is to sweep the coverage area with the power-limited satellites, which prevents the system from illuminating all the beams simultaneously. Considering these limitations, we differentiate two management stages. One is to transmit the common signaling by broadcast beams, and the other is the transmission of user-specific information with data beams. And in this activity, the objective is to design the broadcast beams and the corresponding beam hopping pattern. If you could go to the next, please. Okay, for what concerns the beam design, we have compared four different strategies that are represented in the rightmost figure. First, the option A deploys a reduced number of very wide beams with a small overlapping. Instead, design B adopts a different approach by deploying a very dense grid that, on the one hand, maximizes the ARP, but on the other hand, suffers from high overlapping. So, to try to bridge the gap between these two designs, we have option C that sets interbeam distance between these two limits, and then to enhance the coverage close to the nadir region, a subset of beams is widened, leading to a non-uniform beam distribution. And finally, we have a design D, which is a simplified approach where the number of beams and the overlapping is adjusted with the beam crossover level. If you can go to the next. Okay, so given beam design, and in this slide, I describe the methodology that is followed to design the beam hopping pattern. So first, each beam is assigned to a beam hopping pattern so that beams with the same index are simultaneously illuminated. Another constraint is that active beams should be sufficiently separated to avoid interference. And finally, within the beam hopping period, beams have to be visited at least once. So the proposed solution is to map the beam hopping indices into rectangular blocks, as shown in the figure, and then repeat the blocks across latitude and longitude dimensions. For what concerns the numerical assessment, we compute the minimum number of hops required to illuminate 95% of the coverage area with minimum SINR of 3 dBs, just to mention that different values can be selected depending on the objective. And with these numbers, the numerical results provided in the table indicate that the design B, which focus on setting the number of beams but modifying the beam crossover level, becomes the most efficient solution because it minimizes the number of hops. If you can go to the next, please. Okay, in the next stage, we have investigated how to allocate common signaling into the proposed beam hopping pattern. And signaling here includes synchronization blocks, system information, control channel, paging, and random access messages. The size of these signals have been obtained from 3GPP technical reports. And the proposed solution is to co-schedule common signaling in the slots that are used for SSB transmission so that the SSB period becomes the beam hopping period. Then in this case, in one frame, the UV could perform measurements, decode system information blocks, and monitor control channels that schedule paging and random access messages. If you go to the next, please. Finally, I have represented here the allocation of the common signaling in the proposed design, assuming that there is one SSB transmission per slot in the synchronization block. To evaluate the performance of the overall beam management, we compute the coverage ratio, defined as the percentage of beams illuminated within a beam hopping period, and the common signaling efficiency, which is the number of slots that can be used for data transmission. It's important to remark that we have compared two beam hopping strategies, design D, which is the most efficient in terms of number of hops, and then design B, which is treated as benchmark because does not involve any layout optimization. The numerical results provided in the table indicate that coverage ratio in both designs is 100%, while Design D significantly reduces the overhead, which means that there are more resources available for data transmission. And the recommendation from this analysis would be to adopt the Design D with the proposed methodology. That's it for this part. Next we can move the user-centric beamforming that will be covered by Alessandro.
Yes, good morning to everyone, and thank you, Màrius. So with respect to beamforming, our objective has been that of dealing in details with cell-free massive MIMO solutions over NTN, taking into account traffic-driven coverage principles. So in this graph, you can see basically the high-level overview of what we performed. So taking into as an input the architecture previously introduced by Tomaso and clearly 3GPP specifications, we first designed the algorithms and then taking into account power constraints on board. And this allowed us to basically perform a first round of high-level trade-off assessment at system level with uniform traffic and user locations without taking into account any specific scheduling algorithm. Then we moved in the purple path that you see there, thanks to Professor Foggi from the University of Parma, to a link-level design and assessment, taking into account both OFDM and OTFS solutions. While in the lower part of the diagram, we went into more details of the system-level analysis by designing a pretty flexible database model for non-uniform traffic and user locations that we fed to a scheduling design phase, taking into account both AI and non-AI based solutions. And in the non-AI based solutions, we also took into account distributed antenna systems from space, so federated solutions for cell-free MIMO. So going to the next slide, we basically developed in the non-AI based solutions two schedulers. One on the left is a slightly modified version of a priority queue scheduler. So we just define multiple priority classes based on the unmet capacity, residual unmet capacity, and residual visibility of a standalone satellite for the users. And in the, as you see, the red feedback arrow in the figure, there is an information taking into account scheduling constraints. In particular, we define one based on the channels. So avoiding scheduling in the same time slot users that have channels that are too similar to each other, because that leads to ill-conditioned channel matrices, or geographical position, so avoiding scheduling users that are too close to each other. These scheduling constraints have been maintained also in the more advanced scheduler that you see on the right. In this case, the priorities are not defining classes, so a little bit generalizing the user requests, but they are defined on a per UE basis, taking into account, again, unmet capacity and residual visibility. So going to the next slide, you can see the performance. Well, we run a quite massive simulation campaign. First of all, in terms of the scheduling constraints that you see on the left, with MMSC algorithms, but also a conventional digital beam steering approach, so a conventional beamforming. All in all, the approach designed with a priority rank scheduler, so the per UE approach, is providing an improved performance in both the achieved capacity and the residual unmet capacity. As expected, channel scheduling constraints are providing a better protection against ill-conditioned matrix conditions compared to location-based solutions. What we also observed is that when we go to very dense traffic requests, in particular in terms of the minimum capacity that the users request, we start to have some relevant unmet capacity levels. So this is suggesting that probably some adjustments in terms of the overall system definition may be needed in terms of power, number of UEs served simultaneously, or go into more advanced solutions like federated beamforming and AI-based schedulers. All in all, federated solutions that you see in the central figures show a significant performance improvement, both when all the cooperating satellites use their maximum power, but also when we have an equal power fair comparison. So, for instance, if we have two satellites, each transmits at half the power of a standalone solution. Now, going to link level analysis in the next slide, the work has been basically framed into adaptations and design at air interface level, in particular designing and specifying the OTFS waveform to fit a 5G new radio grid, as you see on the right. A novel detector has been designed based on interference cancellation and message passing principles for both OTFS and OFDM. The performance assessment was performed over a I2R channel model that you see on the slide, and it was included into the software simulation by taking into account as an input the system level capacity performance that we obtained in the previous analysis. So in the next slide, you can see some of the major results. So the performance was assessed in terms of the pragmatic capacity, so no coding and no iterations between the decoder and the detector. In general, OTFS is performing better, sometimes slightly better compared to OFDM, in particular for single satellite scenarios, but actually we do have the saturation of the mod code schemes, so higher gains can be expected. In general, it was also observed that non-coherent combination of signals at the receivers when we have multiple scenarios can be pretty detrimental for the performance. So in this case, some advanced solutions also taking into account multiple antennas at the receivers may be designed, may be useful. And okay, in general, the performance in any case is pretty good, as you can see from these slides. The last analysis that were performed in the next slide were related to AI scheduling. So in this case, we assume that a two-step scheduler, basically. So at the very beginning, we cluster users together based on either their channel vectors or geographical locations, and we consider multiple scheduling algorithms, k-means, spectral clustering, hierarchical scheduling, and dbScan. Then we have a two-step scheduler in which first, if the number of clusters is, which are beams for us, basically, is larger than the number of simultaneously active beams that we can support in the system, we have first an inter-cluster scheduling. So we first have to identify which clusters will be illuminated. And once we identified which clusters, so beams we shall illuminate, we actually select one user from each of these clusters. So we go into the intra-cluster scheduling phase. So in the next slide, we have some results. In general, what we observed is that in this case, location-based solutions, in particular hierarchical and k-means algorithms, are providing a better performance. And they are relatively simple also in terms of the big O complexity that you see in the figure. The motivation for this is that when we go to channel-based clustering, we have a very large number of dimensions in which the clustering has to be performed. So in that case, we basically enter into the well-known dimension curse of dimensionality. So the problem is the number of dimensions. And in that case, location-based solutions are better performing. An exception is spectral clustering, because in that NDB scan, because in that case we can reduce actually the number of dimensions. So we go back to a low-dimensional space. So basically, hierarchical and location-based k-means are the best performing solutions when we go to AI-supported scheduling. I think this was the last part from my side. Yes, please, Luis.
Okay, thank you. I am Luis Blanco. I am senior researcher at CTTC, and I will present the results of the activities related to the data-enhanced radio intelligent controller for radio resource management. Next slide, please. The scope of this task has been the conception of the radio intelligent controller for non-terrestrial networks with an architecture that is mainly based on Open RAN. Within this context, the radio resource management is optimized via two different entities. One is the non-real-time RIC that manages operations with closed-loop timescales above 1 second. This involves some applications such as terrestrial, non-terrestrial load balancing or traffic offloading, and it's normally placed on the ground segment due to the large timescales. This normally deals with some parameters such as, for instance, the beam erbs or the satellite bandwidth. We also have the near real-time RIC entity that works below 1 second scale. This implies normally deals with radio configurations of the GNOD B, such as, for instance, resource block scheduling, beam assignment, or power control, and could be placed on the ground or on the space segment, depending on the time requirements. Next slide, please. The extension of terrestrial O-RAN concept to non-terrestrial networks is need to face some important challenges because unlike terrestrial O-RAN, we have a constellation of satellites, and this brings some unique constraints. First, in terms of latency, especially in case of geo satellites, because this has an impact on the control plane signaling, the synchronization, and also on the interfaces that would require some buffering. Also because we are going to have a dynamic topology and a high Doppler, and this requires some adaptations in the designs of the physical layer and the MAC layer, and also on mobility-aware scheduling and handovers. We need also to adapt interfaces and protocols. They need to be delay tolerant and allow session persistence and dynamic routing. Next slide, please. Also, these networks, they need to be interoperable with the terrestrial ones, and we have important constraints in terms of the hardware because the satellites have limited powers because they have solar panels. They have limited computing resources because the hardware is protected against high energies. And this implies that the onboard processing capabilities are limited in terms of hosting and reconfigurability. In this project, we have done this analysis that has been presented in this Open Journal of Communication Society. It's a very thorough analysis on the different architectural splits of O-RAN between the terrestrial and the non-terrestrial components and the resource intelligence controller placement. And also on the adaptations needed for protocol designs in order to take into account the latency, mobility, and the resource limitations that we have. Next slide, please. Regarding these architectural splits of O-RAN, that is to say what elements we need to place on ground and what elements we need to place on the satellite, we have several options, and we have analyzed several options. The easiest one in terms of computational complexity is to have the DU on board. Okay, this means having the physical layer functions and the axial layer functions in the satellite. Next slide, please. Another option could be to allocate also the CU. This means to have the full GNOD on board. This will add some extra processing and will add extra complexity to the network load. But as an important appendage, will make easier the implementation of the interconnection between the RAN and the core network. As we can see in this picture, we don't have yet any kind of application layer of caching functions. So we have also another option, that is option 3. Next slide, please. Yeah, that is to allocate the UPF function. This will allow some compatibility. This will allow some compatible satellites computing on board, but of course we'll need some extra onboard processing capabilities. Next slide. Yeah, another important issue that we have addressed in this previous journal I have mentioned, okay, is the placement of the rig, okay, where to place the rig. There is a trade-off between centralized intelligence and latency sensitivity. So for the placement of the rig, we need to consider what are the architectural splits, what are the CU and DU placed on the ground or on the satellite part. Also, what is the information exchanged by E2 nodes and the inter-satellite capabilities in terms of visibility and routing. Just some key trade-offs. Ground-based rigs are easier in terms of the coordination of the AI/ML part, and they provide centralized intelligence. But in this case, the feeder link delays impair, importantly, time-sensitive functions, such as, for instance, beam management. On the other side, onboard rigs, they exhibit a lower latency and they are very suitable for near real-time risk, but they are very limited in terms of the scalability and the resource constraints required in case of large constellations. Next slide. Well, I will present just a couple of examples of, we have devoted a lot of time on developing new AI-based algorithms for the resource intelligence controller for the rig. I am going to present just a couple of examples. I refer interested people to the deliverables 4.3 and 4.7 for further information. First one is related to data-driving bandwidth allocation. Okay, we have developed new models based on Kolmogorov-Arnold networks that are a new type of AI architecture that has been recently presented that substitutes, let's say, the edge functions with some learnable functions instead of the traditional fixed activation functions. This allows us to have very lightweight models, okay, that can be even implemented on board the satellites, achieving very high accuracy compared to traditional ML-based algorithms with a lower number of trainable parameters, allowing faster models. This approach has been presented in IEEE GlockCom workshop that is presented below. Next slide, please. This analysis has been extended to the allocation of PRVs, exhibit also some important benefits in terms of forecasting for the analytics models. Next slide. Yeah, we have extended these solutions based on Kolmogorov-Arnold networks in order to estimate the probability distributions of the traffic and radio sources in non-terrestrial networks. This is interesting because rather than generating a single point forecast, okay, this model that is presented and has been recently submitted to IEEE signal processing letters, it's able to estimate the probability distribution for each time step in the horizon forecast, enabling operators and decision makings to take risk-aware decisions. When compared to traditional static allocation algorithms traditionally carried out, we can see a significant, next slide. We can see a significant bandwidth saving compared to this static allocation. And furthermore, compared to the single point algorithms, we can see a significant reduction on the under provisioning rate. Yeah. This concludes my presentation. As I was saying, I mean, there are more advanced algorithms. This based on the extension of the GANs for federation. I mean, there are some federated GANs for, and we can see also that we have considered multi-beam, multivariate probabilistic forecasting algorithms for multi-beam satellites. I referred interested people to deliverables of the projects, in particular the deliverable 4.7. Thanks.
Okay, then we jump to the networking part.
Yes,
So,
sorry. I think there is a question for Luis regarding the 5G run function replacement. So regarding 5G run function replacement, are you the UCU on board or on the ground? Do you consider how the address? Do you consider how to address the case of failure of lost feeder links?
No, actually, this is the analysis we carried out. Okay, so we did an analysis of all the pros and all the cons of allocating the different architectural entities of ORAN in the satellite segment. And yes, this is one of the problems that arise. But I mean, it's mentioned there, but I mean, we didn't solve it. Let's say we just did a thorough analysis of the pros and cons of the different possibilities.
Okay, thanks.
okay, so we move on to the networking part. So my colleague Benny can take over.
Yes, hello, good morning. My name is Benjamin Barth, so from the German Aerospace Center, and it's my pleasure today to represent the partners that have worked on the networking aspects of non-terrestrial and terrestrial networks in the project. Well, you can basically jump this one too. Thank you. Yeah. So, well, from networking side, we have investigated 4 main topics. First is multi-connectivity, following basically the selected reference scenarios, looking into the usage of various end-to-end paths in heterogeneous networks. Then development of AI-ML-based network management tools for improving QoS solutions and enablers in the architecture, and look, for example, in network slicing and optimization here. Then SDN, software-defined network, control with barrier selections and conditional handover needed in flexible TN and NTN setups. And last, research on the core and network function placement, so that basically parts of the cores could be being placed in the space segment, and then also including multi-access edge computing and the placements of it and the architectural enablers. But the main focus of the presentation today here will be the multi-connectivity part. Next slide, please. The goal of multi-connectivity is generally to make use of multiple available paths in the network to improve the quality of service. And this typically either means to increase throughput or increase the availability, or eventually also optimize the latency performance by making use of one or two or multiple networks. In relation to multi-connectivity, we looked at necessary 3GPP updates or architecture updates, adaptations required for the control plane, look into the usage of transport protocols, or more specifically on multipath transport protocols such as MPTCP and MPQuick. And we developed optimization strategies in this framework, which were basically 4 approaches. One was what we called hot swapping of congestion control and scheduling algorithms that have been selected or can be selected out of a fixed set using reinforcement learning. Predictions following 2 paths. First is prediction using the system load and avoid peaks in parts of the network. Second is predict handovers in the NTN LEO constellation and avoid packet losses and drops in performance there. Last optimization strategy is then joint MPTCP and MPQuick controller, enabling efficient coexistence of the two protocols over the same shared links. Next slide, please. Starting from the baseline scenarios of the project, for multi-connectivity, we could basically derive two main scenarios. One is what we call direct connection and the other one indirect. In direct, satellite and terrestrial GNOPs directly serve the UEs, and then the indirect is more or less a backhauling case where we have a relay node, like a EAB node shown here, that is basically backhauled by different NTN and TN links. In these scenarios, we can have basically combinations of links, could be any shown here, TN and NTN and NTN and NTN combinations. So a UE could, for example, be backhauled by a GEO and a LEO satellite, or by a LEO and another LEO from the same constellation or other constellation. And then we have also the terrestrial network here. Needs to be noted that we are showing an UE here that is a smartphone, but we are also assuming directive antennas, so broader terminals, as they can be then also, for example, mounted on board airplanes and trains. This is specifically then the backhauling case, where the user itself, it might be a passenger on board there or sit in a house that is basically providing connectivity in the backhaul scenario. Okay, next slide, please. For multi-connectivity, our reference architecture is AT-SSS, access traffic splitting, steering, and switching, as specified by 3GPP, where basically MPTCP or MP-Quick is used to provide a connection via 3GPP access and a non-3GPP access. The UPF hosts basically the MP protocol proxy function that terminates the multipath connection before the data network, as it would be usually the case with these protocols. The benefit is that we can make use of authentication functions from the core and have a predefined set of connections. In our case, we have two 3GPP only connections. So, for example, a terrestrial GNOD and an NTN GNOD. In this case, the standard foresees a two-core setup, and one acts as a non-3GPP connections. But we have also looked yet in basically not yet standard compliant, but the extensions that would be needed if you want to consider a single core setup as part of the project. And yeah, for further information, you can check also here in the corresponding deliverables of, yeah. Okay, the next slide, please. For the setup of the indirect or backhaul connection, this could be done either via integrated access backhauling or wireless access backhauling. We can see here in the figure the case of integrated access backhauling, where an EAB donor connects to an EAB node. That is basically the relay. The donor provides the CU, so everything above PDCP. And the EAB nodes themselves have a mobile termination function and their own DU then. EAB allows also for multiple hop, making it also interesting in the space setups. WAP is basically the same, but instead of the DU only, we have the full GNOD on the relay nodes. This, for example, also enables edge computing. Yeah, differences. Well, having this as baseline, we looked at various architectures options detailed in the detailed 3GPP communication stacks and identifying option where to place the multipath protocols. Differences that we looked at were, for example, opening the multipath connection at the UE or at the relay node. Other was the MP termination at the space node or on ground. And well, basically the one benefit here of terminating the multipath connection in space would be that if you have multiple NTN connections, you can distribute your traffic in the space segment, and before going back to the ground, you can merge the traffic here and offload the feeder link. Okay. This is basically the architecture baseline. Then we move to our first scheduling, optimization strategy, the predictive scheduler. based on predicting the load. Well, as general for multipath protocols, but a bit simplified here, we have sockets for each of the links. TCP as shown here for multipath TCP. For MP-Quick, this is a UDP socket. And we have some incoming traffic that needs to be assigned to the two paths. And we have feedback from the sockets. In this case, for MPTCP, for the TCP socket, we get some feedback to make some decision on where to route this traffic. Yeah, we have in order to evaluate and we have basically two approaches here that we followed with predictive scheduling or with AI and scheduling. Is first we include traffic prediction, as it has just been presented by Luis in this previous presentation based on Khan. And then we use also Q-learning applied on the round trip time values from the sockets for a solution that we call them basically AI scheduling. In order for this, for the evaluation, we used Mininet in order to model a host connecting to a server via an TN and an NTN link. Actually, the same approach was applied for all the other technologies and presented in the following. If you continue, we can see basically how we modeled the NTN and the TN link performance in the emulations. We modeled here on the left the delay profile applied to the NTN system and some rate performance on the NTN link. This is corresponding to a LEO system. And then next we see the incoming traffic and the system load on the NTN link together with the prediction applied, and that was used basically as an input for the scheduler. I don't see now. Can you forward? Yeah, and then the next one also. Yeah, so this is on the left. We see the system load applied to the NTN link, and actually in red, this is the traffic prediction that is taken into account for scheduling. And then also on the TN network, we have some data that we modeled the system load based on a railway profile. What we see basically for each day, we see the traffic with peaks during the end of the day. And then we used one day to model it and to evaluate the two solutions here, the predictive scheduling and Q-learning. Yeah. The predictive scheduling was a kind of approach take into account the prediction and provide kind of a load balanced approach where we try to distribute the traffic accordingly. And as the Q-learning was taken into account the round trip time values. We have compared this with a redundant scheduler, round robin, and the default TCP scheduler, which is the mean RTT. And we see here for different file sizes the transmission time needed. As we can see, the redundant follows a bit a different optimization goal. So we duplicate packets for robustness. All the other schedulers try to optimize the file distribution. As we see, they perform quite similar as evaluation. We see that still the predictive scheduler and the Q-learning can outperform the mean RTT, but the gains are not so big, which however makes a difference when we look at the larger transfer times, of course. Nevertheless, we'll see this as a bit as a first intuitive approach, and we will look deeper into the behavior to further optimize the approaches here. Okay, on the next slide, we have hot swapping, also based on MPTCP and investigated in a Mininet setup. An AI agent is basically observing the transmission states and gets rewards for proper decisions. Decisions is to select out of a set of scheduling and congestion control algorithms a proper one for the current situation. The reward is based on good put, jitter, latency, and losses. and is tunable by weights. The selections happens here at an interval of seconds, which is not the usual scheduling decision in milliseconds. And the main aim is to basically have well, to be able to cope with the different heterogeneous nature of the networks at a manageable complexity. So this is in this investigation, the delay on the TN network was fixed, and the delay for the NTN was modeled statistically by typical values for a LEO network. And two schedulers are used in this selection. First is blocking estimation BLAST, which is one option also for MPTCP, designed to avoid head-of-line blocking effect. And the second scheduler is a prioritized approach, favoring one link and using the other one as a backup. The two approaches are compared with two Q-learning approaches, one tabular Q-learning and the other one deep Q-learning, in 15 runs, taking 1 hour training with 60 seconds episodes. And as we can see in the results, and then if you could continue, thanks. In the results, we see that both strategies managed to improve their rewards over time, with a higher reward for the deep QN for the deep Q learning, which basically starts with the benefit from the beginning. In the right figure, we see well, no agent has plateaued in this 1 hour training, and we see also in the right figure there the action policy evolution. So both methods first align, but then diverge again, and both converge actually towards strategy A, which is the BLAST scheduler in this asymmetric topology. But at slightly different levels, which is then basically also the reason why deep Q networking reaches slightly better performance and selects around 87% for strategy A, while the priority mode is only selected then during transient degradations of the primary path, and that's why the performance is improved. From CPU utilization, we can see that deep Q learning comes with a benefit in performance, but by investing more resources, as we see here. So the tabular approach is performing slightly worse, but it is using less resources also. Okay, let's come to the last optimization point on the next slide. Is the joint MPTCP MP Quick controller. Here the problem is that the protocols are acting independently, which leads to concurrent and unspecified use of the resources. We are trying to address this by including a controller at the relay node that is monitoring UDP, which means basically MP Quick traffic and TCP traffic for MPTCP, and controls each of these resources in the NTN and in the TN setup. The controller can either operate in a static mode, which basically is a predefined protocol split in TN and NTN, and in adaptive mode, the controller just also slicing policy when, with variations on the available links. In Mininet, we have set TN capacity to 500 Mbits per second, and the NTN link is varying according to real LEO system, between 250 and 350 Mbits per second, and we have some drops during the handover. Okay, when we look at the results of the controller in the next, we see in the upper figure that the performance for the protocol is varying a lot without the controller, which this is basically the baseline that you see here for each of these traffic types, the throughput achieved on the different links. We see, for example, that MPTCP in the terrestrial case gets more share than MP Quick, And it's varying a lot. And then we see the controller in an equal share mode on the lower figure. Each traffic flow is basically assigned a portion of the capacity, and the split is 50-50 in this case for MPTCP and MP-Quick. And we see that we are perfectly match the modeled scenario also. And here we can actually also see the setting for the NTN network with this variation of the LEO and the drops during the handover. And the controller enabled a perfect split for all of these and for all of the protocols and a fair split among them. Not shown here, but the adaptive mode would basically assign more resources to a primary transport protocols in case of degradations, for example, to MP-Quick, where then more resources, since there are less resources, some protocol would get assigned more resources in this case. Okay, thank you very much.
Okay, then unless there are questions. Yes.
Yeah, in the Q&A box, I'm not sure if the first one is for Benjamin or it's still for Luis because it was done at the beginning of Benjamin's intervention. So we see MNOs already offering NTN to enhance their TN services. How close to today's usage of NTN, in mobile networks are the 5G STARDUST features and architecture? Would adoption require large changes in already deployed NTN infrastructure or in devices?
I think this general project I can try to answer, or Tomaso, would you like?
You can start, Benny, and if necessary, can complement.
Okay. Well, in principle, aim of the project was to look into the frame of 5G advanced technologies, and that's why for all technologies we've looked into 3GPP standard as the basis for development and the necessary adaptations. I think at least from networking side, the necessary, most of the features would work with today's architectures on 3GPP based solutions. Yeah.
Okay, then there is another question regarding the topic of GMB and UPF are both placed on the satellite. What is the dominant challenge in practice? Resource limitation, mobility session anchoring, or maybe operational complexity that needs to be addressed? What needs to be addressed first?
Well, all of them are actually challenges, yes, that we looked at. I think it's similar with the GNOB and the UP. Sorry. Depends a bit on how you do also the satellite system design. So whether you have fixed beams on ground and then you have the UPF moving, or whether you have fixed beams on ground and then you have a handover from each satellite to another, then you would also need to hand over the control plane parts. This is easier when you have system with moving beams. Then this challenge, is easier, but you have other problems to address, like mobility, search and anchoring, and so on.
Okay, and there is a last question that just pop up. For the MPTCP, any consideration of the mobility of the LEO satellites when it's moving out out of the coverage of the use, then everything goes on TN and then select the next satellite again?
Well, from transport, from networking point of view, this is then handled at the lower layers. So it's basically lower layers that that is managing the handovers and yeah, the handovers in the space segment. We're basically starting from a UPF and go to the next UPF.
Okay, thanks.
Okay, I think now we can move on with the last part, the POC and the final demonstration. For this, I would like to give the floor to François Trarieux from Thales Alenia Space France.
Yes. Hello, everyone. I'm François from Thales Alenia Space France, and I was in charge of the IVV activities regarding the proof of concept bench in the scope of the 5G Stardust project. So next slide, please. Yeah. Yes, thanks. So just as to get an overview of the proof of concept that has been deployed in the scope of this project. This is basically the macro architecture of the proof of concept implemented. So in fact, the main intent is to have user 5G network that connect core network and the final end user UE through another 5G network, which is dedicated to some backcoding functionalities with TN segment part and NTN segment part. And then the intent is as first to demonstrate the connectivity from the user networks encapsulating through the backcoding networks and able to connect to a unified radio interface up to the final end user UE. Then assess an effective resource utilization of both the TN and NTN segments, and then characterize different NTN splitting between onboard regenerative LEO payload and resources deployed on ground. Next slide, please. Yes, so as to get, let's say, the main principle applied to implement the bench for deploying and demonstrating then the functionalities of this POC. So the NTN part on the feeder link, it's simulated by an Ethernet connection, and the LEO trajectory is simulated by introducing some delay into the network, this network link. Then the user access service links between the satellite and the UE is emulated by a real propagation simulation through an equipment called Satellite Link Emulator, on which we are able to really to emulate some real radio signal propagation impairments, such as the delay or the Doppler. So regarding the TN part, the TN part is implemented by some RF coaxial cable connections, so between RF front-end devices. Then the different, let's say, software component, system and software component are mostly implemented on either directly on OS server or on virtualized environment. And then the most of RF front-end part are relying on some SDR devices such as USRP module. Then the reconfigurability of the bench has to configure either so 3 splits that have been previously identified on the POC definition. So the first one considered is to have a full GNLB on board the satellite. The second one is to have a splitting with a CU on ground and a DU on board the satellite. And the third one is to have a full GNB on board the satellite with a UPS function of the 5G network as well, also implemented on board of the satellite. All of these splitting are, let's say, configurable on the bench by introducing the delay at different interface between the components and only at the software level. Then in the scope of, let's say, operating of the bench, there was a full remote capability of operating the bench that was located and deployed and installed in task facilities in Toulouse and able to be operated accordingly in the responsibility of partner components remotely. Next slide, please. Okay, so as just for you to get an overview, so the full deployment of the bench, there are 4 networks mainly to consider on the bench. So first, in purple, a data network. In green, let's say signal network, where analog signer are conveyed between RF front end. Then time and frequency distribution network in blue, and then in orange there was a remote management network to access remotely from partners all the components to perform all the configuration and required testing. Next slide, please. So, as to present you the main scenario that has been considered in the scope of this POC and has been demonstrating through the testing performed. So it is defined by the residential broadband architecture applications. So where 2 kinds of purpose are considering. So first, in the intent of some energy saving. So when we have TN, so when the network relies on the TN backhaul resource during the day, and then we switch on the NTN backhaul resource. We switch off the TN backhaul resource and switch on the NTN backhaul resource at night, where the, let's say, the data consumption is considered less important. And then second part of second declination of this scenario is to have support of the terrestrial network in a large and sparsely populated area, where the coverage can be limited, and when it's worth to have the opportunity to rely on the NTN resource to provide or to support the 5G coverage. In the scope, of the, let's say, the coexistence of these two resources, we have considered hard handover capabilities, which means when we have a switchover between terrestrial and non-terrestrial resources, we switch all the traffics at all time. So when we switch over to the TN and reverse it to the NTN, all the traffic is switched in the same time. We don't have overlap between. We don't have any traffic overlap between the two resources. Next slide, please. Okay, so as a general context of the preframe of the scenario, so we have considered Unix TN cell and also NTN LEO, so consider quasi Earth fixed cell. So we have there is a loop back LEO trajectory profile of a duration of approximately 5 minutes. Providing a range of elevation visibility to VUE between 20 from 20 degrees up to 90 degrees. And also the final end user UE as a starting positioning, there is no dynamicity considered at the final end user UE. So the overall testing and implementation. So the testing is aiming to assess the end-to-end network connectivity and network link, let's say, performances, functionality compliance from user experience level, which means we try to assess the functionalities from the final end user UE level. The kind of traffic load data applied to the end-to-end network traffic, where some TCP and UDP flow instances. So each flow instance, each flow are specified at 1 megabytes in order to prevent to any over let's say diminution of the link integrity and able to really assess and identify what are the impact of the switchover on the link, and we scale up during the testing. We scale up from unitary one-way traffic flow stream up to simultaneous bidirectional strip of TCP and UDP flow instances. So which means at the end we get both 1 megabytes TCP half duplex and in the same time both 1 megabytes UDP also full duplex. So then just a standard sequence that has been applied, but this is a cycle that depends on the opportunity that has been repeatedly 2 or 3 times. We consider the TN as the nominal resources. Then we switch back we are switching to the NTN resources, and then after some proper duration to collect the data, we switch back to the NTN resources. But the cycle can be extended depending on the opportunity, depending is we are still in a proper visibility of the satellite, and we can still perform sometimes in the frame of the low trajectory profile that is reading at the bench level. And during this sequence, there are some couple of KPIs and metrics that are continuously monitoring and logging. So the latency, so in fact is the RTT, the round trip type with ping utility, the throughput that has been collected with hyperf tools. Also as well for packet error, UDP-GPR, and also we get the opportunity to monitor what is the behavior of the congestion window mechanisms from TCP and how it reacts during the different switchover of the network. And also all these testings were performed across three end-to-end functional on-board split configuration that I have presented a couple of slides before. So next slide, please. So as to first the first KPI. So the first KPI to present is connectivity. Let's say the connectivity by itself, no network performances are considering in the scope of this KPI. So what we can see, so at the level of ping measurement during a switchover, there is no gap in the connectivity that is occurring. So this is an average measurement. Each point relied on tenths of approximately tenths of floating points. So as you can see, it is considering that the switching at let's say connectivity RTT measurement is performed in a frame of 1-2 seconds without any gap. And then the related latency magnitude. So so with the architecture and many let's say as we have 2 radio nodes with the backhaul and the end user networks. So on terrestrial networks, the global latency is a little bit more than 50 milliseconds. That jump up to 60 milliseconds. So 60 milliseconds on terrestrial parts. That jump to 100 milliseconds range on NTN when we relied on the NTN backhaul segment. For the purpose of the testing, to be able during the testing to clearly identify either if the traffic is going over the terrestrial or the non-terrestrial path, we had a 200 milliseconds offset. That's why you are noticing some value of 300 milliseconds on the plots, but the range is 60 milliseconds for the terrestrial network parts and 100 for the space segment part. Next slide, please. Okay, so the intent is to provide some highlights notice, the major highlight notice from the measurement. So as for the UDP part, what at first we can notice is that the network link integrity is always preserved. So we never faced any break on the link on the throughput. Obviously, we get some let's say some drop in the throughput data rates when a switchover occurs. And what we can notice also is that we have an increase on the jitter value also between the frame of a switchover. But this kind of effect are limited to the frame of the switchover. And then we don't. There is not so much disturbance on the next part of the traffic. Besides on the NTN part, the NTN part is less stable than the TN part because even with some pre-compression mechanism applied, it is still critical to get the same stability on the data rate and the throughput than the TN network. So yes, so next slide, please. So yes, what we can notice on for the UDP flow is that compared to the speed 1 is a full GNOT B on board the payload of the satellite. Speed 2 is only the DU part on board of the satellite payload, and so these two speeds were presented before. And let's say the network traffic was really stable despite the switchover frame. But in the case of the speed 3, where we have full GNOT B plus UDP function of the 5G network park integrated on board of the satellite payload, we can notice that we have some many more variations on the data throughputs. Not only limited, strictly limited on the switchover frame, and also we have noticed, even if it's not so significant, but it is only on this speed that we can notice really some packet losses. So maybe one speed. So maybe it's not fully related to the speed, but maybe it is more related to the way that has been used to implement this split on the bench, because on the bench the GNOT B and the UDP, the UPF, are not locating on the same machine. So maybe having these two components located on two machines have bring or amplified this kind of disturbance on the network link. Despite that, these variations, we can see we still have that throughput data rates that remain between some practical value in terms of an application or services. Next slide, please. Okay, so for the TCP part, also we can notice that as for the UDP, the network link integrity is preserved. Besides the variation and the drop on the data rate may be more significant than in UDP, that can be noticed when the switchover occurs. But despite that, there is no breaking on the links and few losses and packet retransmissions. So And then apart this range of the switchover, the data rate and the throughput remain very stable. Next slide, please. Yes, so just to compare the previous slide on the speed 2, and it's especially noticeable with characterization of the congestion window value from proper to the TCP protocol. So the speed 2, where we are only the DU on board of the satellite, there is a very good flatness, even on the switchover frame, compare than the other splits. And as we can see, we are not so much. We are not even almost not dropping or reset, let's say resetting on the congestion window sizing. So next slide, please. Yes, so as final remarks regarding this testing campaign, and we can conclude that it has allowed to demonstrate the compliance of the proof of concept with this kind of residential broadband scenario. So besides, we have seen there is some side effects relating to the switchover. Globally, the link integrity is always maintained, and in this kind of scenario, if we have some let's say throughput variations, it can be easily mitigated. So we can consider we have seamless network link handover capabilities through this spot and related architecture definition. Then it will have be relevant to further conduct some assessments of this POC by plugging more real end user application services such as VoIP, rebooting, file transfer, maybe to assess how they comply to the jitter variation or the throughput or throughput variation as well. Anyway, this kind of work was partially done, especially in the scope of the FUSECO 5G-STARDUST showcase in November, when we demonstrate video streaming on end-to-end network connection across the bench. Okay, that's all regarding the work package about the proof of concept and its testing and validation.
Okay, thank you very much, François. I don't know if there are any questions. We're a bit late, but if possible, we can also take them. If not, I think I can move on with the last couple of slides just to sum up a little bit the main achievement that were just presented. As we have all seen, we achieved to reach a very mature state for what regards the architecture definition with the capabilities of integrating both terrestrial and non-terrestrial networks according to the different say recommendations and insights from the 3GPP specification across release 17, 18, 19, and the ongoing 20, especially in what regards to the support of regenerative payload embarking 5G capabilities. And then from a technical standpoint, different activities are being conducted, at least for what was showcased this morning in relation to beam management, user-centered beamforming, and AI-based RRM. And then for the networking part, some focus has been given to the result achievable once AI-based functionalities in terms of scheduling are plugged into multi-connectivity protocols like MPTCP and MP-Quick. Last but not the least, as just shown in the last 15 minutes by François, we were also able to conduct a successful label demonstration showing really the capability of such an integrated setup where both TN and NTN plays an important role towards the distribution of data depending on availability of resources on either terrestrial networks. Then just to sum up in a few points, the main lesson learned, it's quite clear that the overall ecosystem is very complex, so that it's important to understand what are the challenges, technical ones that may arise when we are going to integrate two domains that are by nature very different, so the satellite one and the terrestrial one. And this respect obviously has been a major point to be aligned with the activity conducted at standardization level in FGVP, and also to support and to influence up to a certain extent the work there based on the inputs and the results achievable in this and obviously in other related NTN projects. In this further consideration is to be taken into account that the excellent cooperation with the industry, being part of the consortium of 5G-STARDUST, allowed us to reach a kind of win-win situation. And in general, this is, I think, a good recipe for future activities in order to have quite alignment between what are the research interests and also the industry development targets. And last but not the least, it's important to take into account that while developing a POC and in general a product, different competencies are needed from the different parts composing the general 5G ecosystem, so from the RAN to the core network, through the different aspects at the physical and networking level, and obviously with all the components needed for the integration of both hardware and software components. Thinking light about the next steps, obviously not in the scope of the project, because the project unfortunately is already over since a couple of weeks, but that can be addressed in other projects, in other activities, either collectively or individually within a specific organization, routing and network management, integration of a real satellite link in order to achieve even more impressive and to complete the demonstration campaigns. And last but not the least, in the framework of demonstration campaigns, of course, would be of absolute value to include the verticals with the corresponding stakeholder in order to show what are the actual added value of such an integrated setup when we are bringing together the system, the technology, but also the user, that in this case would be mostly industry and society. So that's all. Thank you very much for the attention. I know we are quite late. If there are still some remaining questions, we can take some remaining time to address them. I see that
we have 3 people with their hands raised. I asked them to write the question in the Q&A box, but they didn't do it. So if you agree, I can give them the rights to talk.
Yes, please, let's go ahead with giving them the right, and we can extend until 12 so that we have still 15 minutes to address all there and any further possible comments.
Okay, so I'm giving the right to talk to Eddie Gonzalez. So Eddie, please enable your mic and now you can talk. Eddie? Okay, nothing. So I will move on. Okay, no. Eddie, go ahead. Please make your question. Eddie, I see that your mic is enabled, but we cannot hear you.
Okay, maybe we can move on with the next questions if there are
Okay.
any other, and then we
It
go
seems
back
he
to
didn't have
Anthony.
any question. Perfect. So Gunther, I'm giving you the rights to talk. Please go ahead. But it seems that also Gunther disappeared now. Okay, perfect. Then there is only one more question in the Q&A box. Among the three split option, what is the conclusion of pros and cons from the demonstration results?
Okay, I think that this can be taken by François, if you can.
Yes. So from the demonstrations, the pros and cons of the three split. So as we noticed, in fact, let's say the splits that have showed the best performance was the split number 2, when we have only the CU on board. So maybe because we have less processing affected to the delay, in fact, and also in terms of let's say a short-term horizon, that is only implementations really applicable at an industrial level. Then the main target is a full G0 B on board. Let's say it's between the performances are between the both over splits, but it require more processing about the satellite, and also we can notice it's much affected to the delay. And then the last part, the split number 3 will be the most complex. So as we can beside of the POC definition, it's the most complicated configurations to implement on board a satellite payload, because it required a lot of satellite processing. But also it's more complex because when noticed on the POC, it was this component were not simulated as let's say one machine as a one satellite payload, but we try to plug either a part of the G0 B server and a part of the UPF of the 5G core network. So getting only the UPF function. So as the first stand, it is the first split is the most complex one to simulate on a bench or on a POC level, and then it will be the most also challenged configurations to implement in a real industrial deployment. So to conclude, the split 2 is the best, let's say, is the best configuration easiest configuration to implement, but it is a deviation from the standard. So this is the main con. So this is not this is a deviation from the 3GPP standard right now. So this is the main con of this implementation. The second one, the full G0 B on board, it is the best compromise between the two configurations, as there is no deviation regarding the interface specified as defined as the CGPP standard, but it's showing let's say more challenge to implement and to get proper performances. And the last one, it's let's say the most complex one ever to define, to properly simulate on a bench or on a POC, and then to implement on board on the satellite, as we get a lot of processing to manage facing propagation impairment on board on a satellite payload. I hope I get you an overview of a pro and con of the three split from the apprehension we get from the Swiss on the Swiss split from this demonstration and testing campaign.
See, I will give you the rights to talk, so you can follow back with your more question.
Okay.
Hi, thank you. Can you hear me?
Yes, perfectly.
Sorry, I'm asking the question on the chat. Yeah, just I thank you a lot for this detailed explanation. So the only remaining question is, you mentioned Split 3 has very complex processing. It's very challenging to be deployed this on board a satellite. So, so what would be the main advantage if we are going for this solution? So in case we say, okay, the satellite operator maybe can afford to have this option to implement this on a powerful satellite, but what would be the key benefit with this option compared to the Split 1 and 2?
I guess it's more relying, so maybe on the what was let's say discussed before, the definition of the POC, but getting most of the, let's say most of the processing on board of the satellite, getting let's say more capabilities, flexibilities in the resources, traffic network resources management inside the constellations. I guess when you can get some processing up to the UPF functionality, you don't have to rely so much on ground of the on ground resources than the over two splits. So you are reducing the latencies on the service link, so from the satellite to the UE, and I think you can have some flexibility to be able to manage directly some routing only at space level, and not have to rely on the so much on the on ground resources than for the full G-Node B and the CUDU splitting.
Okay, that's clear now. So if I understood right, so among all these three, your recommendation is Split 2 is the best compromise among them. You have the most effective but less processing required on board.
Yes, the compromise is the Split 2 configurations, but right now it's a bit challenging in the space industry to implement so much processing on a LEO payload. So at the short-term horizons, the target is Split 1, and let's say up to 5 years, the target is Split 2, and up to 10 years, the target is to be able to implement Split 3 on board of a satellite.
But sorry, I didn't understand. So the Split 1 have full G-Node B on board actually require more processing than Split 2,
no,
right?
Split 1 has only the DU part on board.
Sorry?
No, Split 1, yes. Split 1 is full G-Node B. Yes, sorry. I reverse. So yes, Split 1 is the best compromise, full G-Node B, and Split 2 has only the DU part on board, and so less processing. Yes, so Split 1 is the best compromise between the two split, and Split 2 is we didn't define the split according to the complexity. In fact, it will have maybe better to define them like that. But yes, split one is the best compromise between complexity and performances. And this is what we have noticed through the demonstrations. And split two has better performances, less complexity to be integrated, but you have less flexibility to be able to do some routing, standalone routing, and network management on the only at space segment level, and you have some deviations. It's a deviations for the actual interfaces specified by the 3GPP standard also.
Okay, thank you. So I understand. So I think that means split one is the best compromise solution, and
yes,
short time for the operator, and split two is in 5 years, and split three is in 10 years. Kind of.
Yeah. So split one is a short. Split one is in up to 5 years. Split two is short-term horizons, up to 3 years, let's say, or actual constellations already in development. And split three, it's a 10 years horizon.
Okay, so means all the current operator are mainly consider split one for deployment.
Sorry?
So the current implementation or the selection of the operator to go for mainly split one in the short term.
Yes. The main thing is that the split one is a little bit challenging for right now to be able to have the right compromise, on in terms of energy consumption, processing load to manage inside LEO payload satellite sizing. So right now we need more, let's say, component efficiency to have a proper running of proper performances running on board a satellite for split one.
Okay, thank you very much. Thank you.
You're welcome.
Okay, thank you, Xi, for the very interesting question, and François for providing more details. I think now we are at the end because it's 12 o'clock, so we largely exceeded the planned duration, but I'm very happy that there were questions that the overall presentation resulted very interesting. So with this, I would like to thank all the participants that enjoyed this presentation today, and more importantly, I would like to thank all my colleagues that made possible the show today, as well as all the other colleagues of the project that obviously could not show up today because otherwise it would have been too many that work hard together with us in this 39 months of duration of the project and allowed to reach these very exciting results. Thank you all, and obviously if you have any question after digesting this presentation, you can reach me or the colleagues of the project by email so that we can have a further exchange or provide you with additional clarification. Thank you, and have also a great day. Bye-bye.